In this video, we'll evaluate limits and check continuity for multivariable functions. So let's start with the first one. Limit as x, y approach 2 and 9 of 101 is 101. Nothing changes. X and y are not in the function, so that's it. Let's check limit as x and y are approaching 6, 2. What that means is x is approaching 6 and y is approaching 2 of x squared minus 3xy over x minus 3y. Well, if we set x equal to 6, we get the numerator 36 minus 3 times 6, 18 times 2, 36 over x 6 minus 3 times y is 6. So we actually get 0 over 0. So let's try some procedures that we learned when we were doing one variable functions. So I'm going to factor out from the numerator x, and I get x minus 3y over the denominator x minus 3y. So x minus 3y cancels with x minus 3y, and we get limit as x and y are approaching 6, 2 of x, which means just 6, because x it's approaching 6, so we replace x with 6. Let's take a look at another problem. Limit as x and y are approaching 1 and 2, so that means x is approaching 1 and y is approaching 2, of square root of y minus square root of x plus 1 over y minus x minus 1. So if we substitute x and y into the expression, we get square root of 2 minus square root of 2 over 2 minus 1 minus 1. So we do get again 0 times 0. So we employ some mathematical processes to do these problems. So what I'm going to do, because I see here radicals, I am going to rationalize the numerator. What that means is I'm going to multiply by square root of y plus square root of x plus 1 over square root of y plus square root of x plus 1. So we multiply top and bottom. So what we get is, so we are still calculating limit. As long as x and y are in your problem, you have to write the limit. So the numerator, I'm going to use the formula a minus b times a plus b. It's a squared minus b squared. So we get square root of y squared, that's y, minus square root of x plus 1 squared, that's x plus 1, over the denominator, it's y minus x minus 1 times square root of y plus square root of x plus 1. So now we notice that the numerator, if we open parentheses, we get y minus x minus 1, which is exactly this denominator. So we end up with 1 over, and if we replace y with 2, we get square root of 2, plus if we replace x with 1, we get square root of 2. So we get 1 over 2 square root of 2, or if we rationalize by multiplying with square root of 2 over square root of 2, we get square root of 2 over 4. We talked about limits, let's talk about continuity. So a function f is continuous at a point AB, provided that f is defined at AB, and the limit as x and y is approaching AB of f, x, and y exist, and the limit as x approaching a and y approaching b of f of x, y equals f of AB. So let's take a look at the problem. At what points of R2 are the functions continuous? So we have f of xy equals x squared plus 2xy minus y squared. So the domain of this function, it's actually R2. So this function f is continuous on all R2 because there is no restriction, there is no problem, there is no point where the limit doesn't exist and is not equal to the value of the function at that point. How about this function? So f of xy equals xy over x squared plus y squared if x is not equal to 1 and y is not equal to 1, and 0 if xy equals to 0, 0. So let's check the continuity at 0, 0. So let's find the limit as x and y are approaching 0, 0 from xy over x squared plus y squared. So if we set each of them equal to 0, we get 0, 0. So let's try path y equals mx. So let's see what happens. So for the path y equals mx, we get limit as xy is approaching 0, 0 of x times mx over x squared plus m squared x squared. So if we factor out x squared from the bottom, we get m over 1 plus m squared. So basically, if m equals 0, we get the limit to be 0. If m equals 1, we get 1 over 2, the limit. So because we get all these different values, then we can say that the function f is not continuous at 0, 0. Let's calculate another limit. Limit as x, y, z approaching 1 ln 5 and 3 of z e to xy. So this is, let's replace each. So this is x, this is y, and this is z. So we get 3 e to 1 ln 5. So that is 3 times e to ln 5. When the base and the argument of ln are and the base of the ln are the same, we get just 5. So it's 3 times 5, which is 15. And finally, the last example, at what points of R2 is the function f of xy equal to square root of 2x minus y over 3 continuous? So first of all, let's find the domain of this function. So to do that, we set 2x minus y greater than or equal to 0 because these functions are in real numbers, so the radical has to exist. So that means negative y greater than or equal to negative 2x or y less than or equal to 2x. So if I were to graph this, I would graph y equals 2x, which is, so okay, let's put the arrow this way away also. So oxy, so 2x would be if x is 0, y is 0, if x is 1, y is 2, if x is 2, y is 4. So we would have a line like this. This would be y equals 2x, but y less than or equal to 2x would mean the region under the line. And we can think like this. If, for example, x is 7 and y equals 0, we get 0 less than 14, but 7, 0, it's 1, 2, 3, 4, 5, 6, 7. 7, 0 would be this point, right? So to satisfy that inequality, we are choosing the region that is the green one. So basically the domain is actually, so the domain is xy with the property that y is less than or equal to 2x. And actually, at what points on R2 is the function continuous? Well, the function is continuous on all the points in the domain. So the function f is continuous on all points in the domain D.